Hello everyone, welcome to part 23 module 2 computer networks. So we were discussing so far the carrier sense multiple access protocol with the collision detection, one of the media access control option we have. And now we moved our attention to a different set of protocols coming under the name collision free protocols. So as we already seen in case of CSMA, chances of collisions were there, and once the data get collided, and we will do a systematic procedure to detect it. Now what about collision free protocol? The word itself says that they are ensuring there is no collision at all. And how they are achieving it, let's see. Although collisions do not occur with the CSMA bar CD, once a station has unambiguously captured the channel, they can still occur during the contention period. I mean, once a station captured the channel, further collision chances were there, not there. Let's take the pen. Yeah. They can still occur during the contention period. Contention period, you are knowing, like when all stations were trying to send data. So everyone is contending for the media, the access to the media, and that time chances of collisions were there. But once you carefully send the data, and so the one station has unambiguously, so that is something important. So without any confusion, I am getting the exclusive access to the channel, I am capturing the channel, then the chances of collisions are not there. But definitely such cases are rare. Most of the cases during contention period itself, more than one station may try at the same time, and it will result into collisions. So that about the general scenario with the CSMA bar CD. Then these collisions adversely affect the system performance, of course, especially when the bandwidth delay product is large. So how it is going to affect the system performance? When there is very good bandwidth and I mean length of the cable. So that is what makes the term bandwidth delay product. When it is large, we have enough resources. So that is what it indirectly says. And or otherwise the cable is long enough with the enough bandwidth, and that time the performance will be very less. And the performance analysis of CSMA we already seen, and we know that equation where you can see that as the length of the cable increases, its performance is start decreasing, and also when the frames are short, again the performance is poor. So to get better performance in CSMA bar CD, what is needed is a long frame, or the length of the frame should be long enough such that the collision signals when it is coming back, the sender should keep sending the data. And also to make it possible, the length of the maximum distance between two machines in a typical LAN running under CSMA bar CD should be small enough. So when the frame length is short, or the cable length is long, you can expect an adverse effect on CSMA bar CD protocol because of this collision. And not only do collisions reduce the bandwidth because of this retransmission and all, but they make the time to send a frame variable, which is not a good fit for real-time traffic such as voice over IP. So you know, for real-time traffic, the time limits are very important, right? So what we need is a fixed time kind of setup. But you know, if you run it using CSMA bar CD, the time frame will be variable, in the sense on time during the first attempt, the amount of delay that you are experiencing may be different for the second setup. So in that way, it is not a good choice for real-time traffic. So altogether, we need a better system that supports real-time traffic, and also for LAN setup with a very good bandwidth delay product, we need a better performance. So that is our ultimate intention. So as CSMA is not providing such guarantees, they are not universally applicable. In the sense, we can have local area networks with CSMA bar CD, but we can't generalize it to any kind of setup. So next, let's study some protocols that resolve the contention for channel without any collision at all, not even during the contention period. So CSMA bar CD, we already seen the type of collision that we can experience during contention period. And next, what we are going to see the protocols which run without any collision at all even during contention period. So there is nothing like collision there. So how they are handling it? So we start with the first protocol, the Bitmap Protocol. I think it is better for us to see an example, or just let's go through the statement and then example. So in the first category of the collision-free protocols, we will examine the so-called bitmap method, where each contention period consists of exactly n slots. So like that we are assuming the contention period is having n slots. Now if station 0 has a frame to send, it will transmit 1 bit during slot 0. So n slots, each slot corresponds to one station. So slot 0 is for station 0, right? And similarly, no other station is allowed to transit during this slot. It is exclusively for station 0. And if station 0 want to send a frame in subsequent communication, it will be knowing it, right? And that time it will transmit a 1 in slot 0. Similarly, regardless of what station 0 does, station 1 gets the opportunity to transmit a 1 bit during slot 1. So slot 1 is dedicated for station 1 and slot 0 is for station 0. Like that, slot 2 will be for station 2. So whoever want to send some information, I mean whoever is having a frame to send, they will send a 1. So that 1 in that particular slot is indirectly informing all other machines that this particular station want to send. So others should keep silent during that time. So in that way it is controlling collision. So in general, the station J may announce that it has a frame to send by inserting a 1 bit into slot J. So slot J is for station J. So if station J has some frame to send, it can announce it to others by making this particular bit corresponding to that slot 1. So after all n slots have passed by in this manner, like slot 0, slot 1, etc. corresponding to station 1, station 0, station 1, so on. Now each station has a complete knowledge of which station wish to transit by looking at that. That is why it is called a bitmap. So you can call that particular frame to be a bitmap. So each bit represents whether that station corresponding to it is wishing to send a frame or not. Now at this point, once the bitmap being communicated, the actual transmission of the frames will happen in the numerical order. Like a station 0 want to send, then that bit will be 1. Then station 0 will be sending first, then station 1. Like that, whoever is having the data, first they will make that bit 1. Accordingly, in that order, in the numerical order, they will start sending the data. We will see that example. Yeah, some more theory behind it. Since everyone agrees on who goes next, there will never be any collision. So because of that bitmap agreement before the actual communication, there will not be any collision at all. So after last ready station transmitted its frame, another n bit contention period began. So the same cycle will repeat again. If a station becomes ready just after its bit slot has passed away, so that is one problem. Everybody will be getting a chance. In that time, suppose the station misses its slot, then it is out of luck and must be silent until every other station had a chance and bitmap has come around again. So that is a problem. So whenever you are getting a chance, if you want the data, you should correctly send that bitmap, update your bitmap information. Then only you are allowed to send the data. Otherwise, you have to wait for for the time being you are unlucky and you have to wait for your next chance. So the protocols like this, in which the desire to transmit is broadcast before the actual transmission, are in general called reservation protocols. So we are doing a kind of reservation, in the sense we are informing others like, this is my turn and this is my turn. No, others please don't send in that way. So we are broadcasting to everyone our desire to transmit before our actual transmission. So such protocols, the collision-free protocols, were otherwise called reservation protocols, because they reserve the channel ownership in advance and prevent future collisions. So the channel efficiency at low load is easy to compute. So more detailed analysis you can see in that text. So And here a brief analysis is given, like so I think we will see example and then this analysis part. So it is something like this. First, this picture has to be clear in your brain. So initially we have that bitmap. So this is our bitmap. So corresponding to the contention slot. So suppose there are 8 stations who wish to send. So each station will be given a slot in the bitmap. So station 0, the slot 0 will be used, and station 1 will be using slot 1. Similarly, now see, station 1 is informing others that I have some data to send. What about station 0 and 2? They don't have any information to send. And another one who is having some frame to send is 3 and 7. So that is this example says, right? Now once this particular bitmap information is being communicated, they will start sending frame in that order, following that numerical ordering. Like numerically who will come first? This 1 will come first. So 1 will be sending its data. Then this 3 will come, 3 is sending its frame. Then 7 will come, 7 will send its frame. Okay, again, one cycle completed. Now the process will repeat, and during the next cycle, again it will start sending their wishes, like the bitmap information. Like station 1 want to send data, so 1 is sending like this. Now only 5 want to send its frame, so 5 is sending this. So this will complete another cycle. Again in the third bitmap only 2 want to send it, so it is expressing its wish like that. So this is just a 1 bit length. Okay, so that is why it is shown to be 1, where this frame length is assumed to be some d bits. Okay, d bits. So if there are n machines who are in the contention period, then the bitmap will be of length n bits. So where n is the number of stations who are participating in the contention. So the size of the frame is assumed to be d bits. So using this d and n, the efficiency derivation is given, say in the previous slide. So at low load, first we will have the efficiency derivation. It is like so the total time by cycle time, right? That is the way we are deriving efficiency. Actually, to send a per station, what is the utilization? Like that we are calculating. To send my own frame, I just have to send a d bits only. But this extra n bits I am sending just to avoid that collision. So this is actually the overhead, right? So the overhead per frame is n bits, and the amount of data is d bits. The problem why n bits is taken completely is, say just like in that example, even though there are 8 slots, 1 or 2 stations were actually sending the data, but even though that is the case, all others are supposed to wait for the transition of these n bits, right? So per station this n bits is coming as an overhead, but when it comes to high load, means the overhead per station is overhead per frame is just 1 bit only, because it will be tightly packed. All those n bits will be 1 when load is high, in the sense load high in the sense everyone wishes to send the data. So accordingly they will make all these where is the picture, all these like 1 bit. So on an average you can take 1 bit overhead per frame for a particular station. But if the load is less, something like this n bit overhead is there for this single frame transmission. Actually I don't want it. I can't say that it is only 1 bit, even though I am only sending the data, this n bit is communicated as an overhead information. But if everybody is sending the data per frame, only 1 bit is actually consumed. So just like if all bits are 1, so assume a situation when the load is high, per frame only 1 bit is actually wasted as overhead. But here per frame n bits are wasted. So that is why we have 2 derivations for the channel utilization. For when the load is less, relatively less, this n bits is found to be an overhead. Even 8 station it is fine, but in general thousands of machines will be participating, and this will simply spend as an overhead. But in case of heavily loaded situation, per frame it is enough to count a single bit in the bitmap. So that is how we are having the derivation. So hope this protocol is clear. So that about the first collision free protocol, the bitmap protocol. Now we will see the next one in the next presentation. Thank you.